All right, Geraint. So I noticed you wrote on your blog recently, your website, GeraintLewis.com, GeraintFLewis.com. Sorry. What's
Don't get me confused.
GeraintLewis.com? I bet that's someone else.
He's a
'Cause
photographer.
there's a few of you around.
Yeah.
Science and the Laconic if.
Yes.
So, well, first of all, what do you mean by the Laconic if?
Okay, so this goes back to a story from sort of ancient Greece. So Philip of Macedon was the father of Alexander the Great, and he threatened Sparta. And we all know about Sparta. We've all seen the 300, and we know basically a warrior city and all that kind of stuff.
The great documentary.
Great documentary, right? So the story goes is that Philip of Macedon, I'm going to paraphrase here, basically said he said to the Spartans that they must submit to his power, because he said, if I bring my armies to your land, I will burn your cities and raise your crops and kill your people. So the response from the Spartans was just if, right?
Yeah.
That if
one of the great comebacks of history. Just
yes,
bad.
yeah. And there was another one, actually. Apparently, Philip of Macedon also said to the Spartans, do you want me to come to your country as a friend or as a conqueror? And the response was neither. So
nice.
So
Trash talk.
So the laconic if is this if. It's a short, terse statement that carries power, right? I mean, essentially, it was almost a threat back to Philip of Macedon, right? If it's not like it's up to you, it's like if you can bring your armies to our lands, then we've got these issues.
Yeah.
So I wrote this thing because there's an interesting discussion that goes on actually outside of scientific circles more than inside, but it does happen inside about what is science. Right? What gets put in the bucket of science and what gets put in the bucket of pseudoscience, and how do you tell the two apart?
Yeah.
And so I wanted to write something about that because I get people saying to me, oh, multiverse. You can't talk about the multiverse. That's not science.
Yeah.
Put that in the science. String theory, right? String theory, that's not science because blah, 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 in the pseudoscience bucket. And I think this comes from a couple of places, right? Firstly, there is a complaint from some aspects of actual scientists. We've seen people write books and blog posts about why they don't like certain ideas. And that gets into like the broader consciousness of, this therefore isn't science. And there's a mistake about where hypotheses come from. So I'm just going to wave my hands around for a moment. So, as a scientist, we're told that there's this thing called the scientific method, right? This is almost like closed circuit where, you form a hypothesis, you do an experiment. If the experiment works, then your hypothesis lives to fight another day. If it doesn't, you put it in the bin and you go around, etc. And you form this loop. And the question is, where do hypotheses come from? Where do your ideas that you want to test come from? And there are some people that are very strict in this definition of where hypotheses come from. They come from your experiments and your observations. So you do an experiment and you produce a result and you make a new hypothesis based on that result and you go through the loop again, etc. But what I wanted to point out is that finding your hypothesis is actually a broader topic, right? It is asking if questions. If something, then the consequences are, right? And that's how you can start to form hypotheses. Now, when we spoke about this, you mentioned that this has got a Latin name and that it's a relatively modernish viewpoint of how we should do science.
Yeah, well, modern in the sense that it came after the scientific revolution, so to speak. So yeah, if you're in the philosophy of science, it's called hypothetical deductivism. So you start with a hypothesis, you deduce from that hypothesis what you think the world would be like if it were true, and then you go and check whether you were right. So hypothetical deductivism. So the interesting thing about this is, as I've recently, as part of actually teaching a course, been reading a bit more about what the people who did the scientific revolution, so to speak. It's not the best name for that period. I don't want to give the impression that that's when science started, because Ptolemy was doing science, whatever your definition of science. He was doing science, and that's, in the hundreds AD. But so, for example, this idea that a hypothesis can come from anywhere. So there's a quote that you particularly like, and I quite like it too, from Richard Feynman, where he's giving a talk, and he says, there's this process to science, and the first step to getting a scientific law is you guess it, and then the audience starts laughing, and he says, no, that's true, and he says, slightly later. It is not unscientific to make a guess, although many people think it is. So this idea that it doesn't matter where your hypotheses come from, what matters is what follows from them, and whether the stuff that follows from them is in fact correct. And reading through some of the sort of history of science, I think Isaac Newton would have disagreed with that. And so he lays out, in his writings, he lays out his sort of rules for science, how science is going to work. So he doesn't just do science in terms of, there's a theory and there's observations, and he explains that, although obviously he does that and magnificently well. He's also got a definite theory about, an idea about how this science thing is supposed to work. And one of the principles of that is, you're supposed to get your hypotheses, your ideas, from observations in some sense. You can then universalize them and generalize them, but they need to come from observations in the first place. So you can't just make stuff up out of thin air. So he's trying to, that seems more restrictive than what we have today, but he's actually arguing against people who thought it was even more restrictive than that in science, that actually you should just describe the data. So there's this sort of, it's called inductivism, sort of Francis Bacon, where the way you do science is you collect a whole lot of observations, and then you just stare at them, and then you keep staring at them. And if nothing comes to you, just get some more observations, and then just keep staring at them. And then a law will come out of those by a process of generalization. So you heat up a piece of metal and it expands. And then you heat up another piece of metal and it expands, and you heat up that piece of metal and it expands. And then, oh, hang on, I'm seeing a trend here. And so you generalize. The way you get to a law is you had all these observations, and then those suggested to you, all pieces of metal expand when heated. And so that becomes a scientific law. Now, Newton doesn't want to do that because he wants to say that the law of gravity applies out in the universe to the way things move in the solar system. And that's not in any sense a sort of easy or straightforward generalization. He's not going, this planet goes around by gravity, that planet goes around by gravity, therefore all the planets go around by gravity. But he wants to show that there's a connection between his hypothesis of gravity and the observations. So what he actually says is something rather confusing. What he says is, those qualities of bodies that cannot be increased or diminished, and that belong to all bodies on which experiments can be made, should be taken as qualities of all bodies universally. And when you think about that for like an entire career and try to explain what the heck he meant by that, what he's trying to say is he's got gravity in mind, and what he's trying to say is, okay, I'm not just jumping out to this, what if there's a force out there, and getting some conclusions from that. What he's trying to say is, okay, we see in the stuff around us this thing called, mass, which is a quality that bodies have, and you can add things together to make more mass, but the mass of an individual particle doesn't change, so it's a conserved quantity. Okay, and we see that mass takes part in gravitational interactions around us, so stuff falls, right? And so I can then take that from my observations and push it out into the universe on a universal scale and make a general law. But I have to have started from observations and then push out to the general law.
Yeah.
And so it's not quite the Laconic if, as you say. He doesn't just, he wouldn't allow a hypothesis to come out of nowhere. So famously, at the end of the Principia in the General Scholium, he says, "What is the cause of gravity?" He's given his equation for gravity, but he asks, "What's the cause of gravity?" And he says, "I frame no hypothesis." Famously, well, hypothesis non fingo in Latin, of course, and he's not just saying, what I assumed he meant by that was, I don't know, we'll have to go and look. But he's not just saying, I don't know. He's saying, we don't have the observations here that I can push out to a universal law to tell me what gravity is like. We would need to find some more observations to do that. It's not that he can't think of a hypothesis to make up that would explain gravity. It's he doesn't have the observations to push out to make a hypothesis. Now, the way he uses the word hypothesis is somewhat, as a lot of people pointed out, it's not quite consistent throughout his whole corpus. But it's interesting that this picture of science, which is the way we do it, and the way you've laid out there, actually took a while to catch on. The sort of, actually, we can't expect our observations to get everything. We can't expect observations to give us the right ladder up to the right hypothesis. Sometimes we just need to start with an idea and test it from there.
Yes. So this is an area where most scientists are very poorly educated, right? Is the philosophy of science and how the actual application of science has developed over the centuries.
Mm-hmm.
One of the interesting things about Feynman's statement is that I think, firstly, he was known for his particular kind of personality. I think what he is also saying is that it's not just any guess that goes.
Yeah.
An educated guess.
Yes.
Right. So it's not that he's pulling something completely random out of a hat. He understood the way magnetic fields and electric fields worked, etc., and he wanted to understand the electron. So he proposed ideas about the workings of the universe based upon his understanding of what we already knew at that time. And this happened with people like de Broglie or de Broglie, or however you want to produce his name. He was the one that essentially people got to the point where they understood that light had a particle nature as well as a wave-like nature. So it travels like a wave, interacts like a particle, right? So you get photons deposit energy at a particular point. So he knew that, and he just said, what if, could spin that around, what if massive particles can travel like a wave and interact like a particle? So that became the birth of modern quantum mechanics at some level. But that was a if-then kind of question, right?
Yeah.
If particles can behave like waves, then I expect I should be able to diffract electrons through crystals and all this kind of stuff.
Yeah.
So it's the if and the then that I think that matters when you're proposing your hypothesis. As you said, you don't get anything by coming up with a hypothesis and then not saying what the consequences are.
Yeah.
Right.
Yeah.
If it's not testable, right, it doesn't fall into that scientific bucket at the end of the day. But the formation of hypotheses is the first step in the scientific process.
Yeah.
Then it's the what's the consequences? Then can we test them? So we've worked on this question of fine tuning, right? Fine tuning of the universe, and you end up in lots of arguments with lots of people. You end up in arguments with lots of people who are not scientists, who just go, this isn't science, because they heard somebody on a blog post saying, this isn't science, blah, blah, blah. But it's hypothesis building, right? So the idea behind fine tuning is, if the constants of nature could have been different, then the universe would have looked like this.
Yeah.
Nowhere in there do we say that this demands that the constants of nature could have been, must have been different, or that, etc. What we're doing is we're building a hypothesis based upon an if. And this, of course, then people say this leads to questions about whether or not there's a multiverse out there.
Yeah.
The multiverse, again, is a hypothesis. And people say, well, the multiverse is not science because you can't test it. But we don't know if the multiverse concept or the hypothesis is testable or not because nobody's developed the mathematical theory of how a multiverse works.
Yeah. Actually,
Don't-
De Broglie's example is a good one there. So he's the 1930s. No one would have thought to look for wave-like properties of electrons if De Broglie hadn't developed the theory first.
Yes. Yeah, exactly.
They might
Exactly.
have accidentally got it, but yeah.
And it's a similar thing with string theory, right? So string theory, which has now been around for like 40 years or so, and people say it's not science because it's not testable. But the point is that what we're told is that, from string theorists and the brain people,
Yeah.
is that the theory hasn't even developed to that point where you can make the assessment of whether or not it's testable or not.
Yeah.
We're not even there yet.
Yeah.
And so there's not this magic moment of when something becomes science because you write down a prediction over there. The entire act of building your hypothesis and then starting to work out the consequences, that is part of the scientific journey. And this journey, people say, well, but this has taken decades. Well, big surprise that complicated things take a long time to develop.
So it is funny that, just getting back to it, that's the modern picture of science that I think a lot of scientists would have, especially in physics. It was just remarkable to me how relatively recent that is. So Newton, as I said, doesn't quite have that picture of science. It's not quite the old just stare at the data and wait for something to occur to you, but he still needs to make room for, why would you think that the gravity works out in the universe? But he's so highly revered, he's basically untouchable for his reputation for an awfully long time. No one's going to disagree with Newton. So there are wonderful books in the early 1800s where, that basically what science is what Newton taught us. Here's what Newton taught us to do. If we're going to do this, is how you do science. But it really kicks off actually in the early 1800s with the previous wave discussion, which was, is light a wave, which at the start of the 1800s hadn't quite been worked out. And the question was not just, the way this is told to us as undergrads in your science training, is there was the idea that it's a particle, there's the idea that it's a wave, and then someone derived from the wave theory, right? There's that if light is a wave, then if you shine light at a small circular aperture, it will go around the aperture and create a bright spot in the middle of the shadow. And that seemed ridiculous. And then someone did the experiment, and hey presto, there it was. Now that was a major moment, but there was a massive a very major methodological discussion around that, which was, okay, if light's a wave, what is it that's waving, right? What's the actual thing that goes? And it must be something that's not just particles. There must be something else that makes up the universe, an ether, a famously sort of in and out principle in physics. They come and they go. And so this now comes down to your methodology. If you go with Newton, we've got no experience of ethers. So there's nothing we can take from our experience to then push out and universalize. There's not like I find an ether in this room, so I can assume there's an ether everywhere. And so on the basis of that principle, that theory is ruled out, not observationally, but because it's not the practice of science to do that. Against that, you had scientists like Young saying, look, we can't guess what the universe is like ahead of time. We just have to explore these hypotheses. And if they have good, the correct prediction is a reason to think that that's the way the universe is. And I think the success of the wave theory of light is not just a success of a theory in physics, but actually tells most scientists that there's a broader, more general way than Newton said of doing science itself, and it's this Laconic if.
Yeah. So look, I'm going to finish on a slightly controversial topic, right?
Ooh,
so
yeah.
I get wrapped up in discussions about AI, and
Ooh,
will AI ever come up with new science? And at the moment, I think the problem that AI has is that it has that Bacon viewpoint, right?
yeah.
Throw me data and I'll give you a law,
Yes.
right? throw data, throw data, throw data, throw data. I can give you a law. I can tell you how this is related to that. And now I can come up with a mathematical equation to explain how the iron bars expand, etc. But AI lacks a creative aspect. And that creative aspect is the hypothesis forming. If this, then that. How do you get AI to think in that way? And think in the same kind of way that de Broglie thought, oh, what if matter can behave like waves? Or Schrodinger thought, oh, I'll just have a guess at the wave equation and see what comes out, right?
Yeah.
How do you build that into AI? And I'm not saying it's impossible, of course, because we don't even know how our creativity works.
Yeah.
Right? We just do not know where ideas come from. But we hear about people who have dreamed up new ideas, right? Where you pull information together and you have that creative step. And I don't know if we know if AI will ever be able to have that creative aspect. I think this is one of Penrose's arguments, right? Is that AI will never create in the same sense that humans can create. They can mimic, but they'll never create.
Yeah, interesting. The example of Schrodinger's equations are really one I have from undergrad days, because this equation went up on a blackboard, and you kind of expect some sort of derivation to happen before then, but it just goes up. And where does that come from? And the answer is out of Schrodinger's head.
Yeah.
That's it. We don't get there from data. That thing then takes us to the data, and then we see if it's correct. So yeah, the AI question is a good one, because you can just throw a lot of data at a computer and it can try and summarize it for you, and it might be very successful, but can it do what if matter was made out of little strings, and then go from there? That's a very interesting question.
Yeah. Anyway, you're going to link the thing I wrote about the Laconic if in the notes below.
Yep.
But yeah, this kind of question of what is science, I think, is an interesting one. And I think it's one that needs to be discussed more broadly.